guys, welcome to the page of Ask IITians. In the last video, we discussed about relations, right? And I told you that in the next video, we'll be discussing about functions. Okay, so today is the time that we start the discussion of the topic functions. So I'm sharing my screen with you guys. I hope my screen is visible to you guys. And as I told you, the today's topic of discussion is going to be functions. Have you heard of this term functions in your day-to-day life? Yes, you might have heard of functions that are happening in your family or in your school or some other festivals that are going on, right? So we colloquially we call these terms as functions, right? But these are slightly different in maths than it's in our day-to-day life. So we need to understand when can we call something as a function. So if you remember, we were discussing relations in the last class, and in the relations, we discussed that it's a subset of the cross product, right? So if let's say I'm having here A, B, C, D, and E, and let's say I'm having here 1, 2, 3, 4, and 5. So let's say if I do the mapping in such a way that A is mapped to 2, C is mapped to 5, B is mapped to 1, D is mapped to 3, and E is mapped to 2, something like this. So here what you can see is that two different elements A and E are getting mapped to 2. So if I write the ordered pairs, what are the ordered pairs we'll be getting here? We'll be getting A comma 2. Next we'll be getting as B comma 1. After that we'll be getting as C comma 5. Right, we'll be getting as D comma 3, right? And next we'll be getting as E comma 2. So these are the ordered pairs we're getting here. We can see there 4 is not mapped to either any of the elements of the first set. Let's say I'm calling the first set as set A and the second set as set B. So this is an example of a function. This is a relation. Yes, this is a subset of cross product. Definitely, this is for sure subset of the cross product, subset of the cross product, definitely that's there. So this is definitely a relation. This is definitely a relation from set A to set B. But when can we say that this relation is a function also? So there is a very important property that we need to understand, that every element, yes, we have mapped A, B, C, and D and E. All the elements we have mapped, we have not left alone any of these. If you remember, in relations, we can leave any element which is not mapped to the other set, right? But in case of functions, every element will have to be mapped. And another important thing is every element will be mapped to only one element in the second set. So the definition that we'll be having here is a relation. A relation is called a function. A relation is called as function if every element of first set, let's say I'm calling it as set A, is mapped to every element of set A is mapped to only one element of set B. So this is very important. The two words that are very important in this definition are every element of the first set has to be mapped and only one, they have to be mapped with only one element of the second set. That is also very important for us. So this is the understanding. This kind of relation will be known as a function. So only this kind of relation will be called as function, not everything. So let's say if I draw basic examples over here, I'm taking few arrow diagrams here, which will help us in the understanding. So I'm taking A, B, C, and D. And here we're taking 1, 2, 3, and let's say 1, 2, 3 only. So if I'm having, I'll just firstly select this because we'll be using this to explain it multiple times. Okay. So let's say my A is mapped to 2, my B is mapped to 1, C is mapped to 3. Here we can see D is not mapped to any of the elements. D is not mapped to element, not mapped. Because this D is not mapped, that's why this is not a function. This is not a function. Right. If I take another example over here. So let's say I'm saying A is mapped to 2, B is mapped to 1, B is mapped to 3, and C is mapped to, let's say, 2. Let's say I'm having 4 also here, and D is mapped to 4, something like this. You can see here, you can see that the element B is mapped to more than one elements. I told you in the definition that it is mapped to only one element. Whenever it will be mapped to only one element, then only it will be a function. Otherwise, it will not be a function. It's not a function. So this is also something that we need to understand very clearly. With the help of mapping diagram, we need to understand what whether they are mapped to only one element or they are mapped to multiple elements, whether each element is having an image there or not, right? So these are the things that will be requiring to understand or comment whether a given relation is a function. And yes, all of these are relations because relation is just simply a subset of cross product. So as long as we are having something like this, so yeah, this is, you can see here every element A, B, C, D, every element is mapped to the other element, right? And if you look at A, map to only one, look at B, map to only one, look at C, map to only one, look at D, still map to only one. We have to look at the first set. Doesn't matter that two elements or more than two elements are mapped to the same element, like three in this case, right? Still, this is a function. This is a function. So yes, multiple elements can be mapped to the same element, but one element should not be mapped to multiple elements. So this is a function. Even if I say, let's say I'm taking 4 also here, I'm taking A with 1, B with 3, C with 2, D with, let's say, again 1. In this case, you can see we have left 4 alone, but that's not a concern for us. That's not a concern for us because the first element, the set of the inputs that we have, they should have definitely one output, right? So if I try to say this in layman terms, firstly, though, this is a function. This is something that we need to understand, that yes, this is a function. What else we need to understand is every input must have an output. Every input must have an output. This is first condition that we need to have. And every input must have only one output, only one output. It should not happen that we are giving an input and we are getting more than one output for that. So we need to have only one output corresponding to every input. If these two conditions are met, then we can say that the given relation is a function. So I hope we are good enough in establishing this definition. Right. So next thing that we'll be having here is function notation. Function notation. How do we denote the function? So let's say a function is defined, a function, I'm giving the name as f, you can call it as g, you can call it as h, anything you can call. I'm calling this function as f. A function f is defined from set A to set B. Then how do we denote that? We write the name of the function, which was f. We use colon over here. Colon we'll be using. We'll write down the first set and then we'll take an arrow and write down the second set. This is exactly how we are going to denote a function. So we'll be reading this as function f from set A to set B. Whatever we written here in the sentence format, we have written this in the compact form over here. So I hope we are clear till here how we'll be denoting a function. Now, important thing to understand here is, like, if you remember, we have studied domain, codomain, range in with respect to relation, right? Now we'll be explaining the same thing with respect to function also. So the next heading that we'll be having is domain, codomain, and range of functions. Domain, codomain, and range of functions. So this is the next title or next heading that we'll be having with us. And now let's understand. This is somewhat similar to the relation that we studied. One slight change is, in case of relation, there might be some elements that will be left in the first set. But in case of function, we will not be leaving anything behind. Everything will be mapped to one thing or the other. So we'll be saying domain of f. We can write the same thing as d of f. In the subscript, we'll be writing f. So d of f is going to be it's a, b, c, and d. The set of a, b, c, d, four elements. This will be your domain. Let's say I'm adding one more element over here. I'm adding here as 4. Okay. Now, if someone asks me what is range of f, we denote this with capital R and subscript f. This is going to be just 1, 2, and 3. 4 is not in the range because 4 is not mapped to any element of set A, right? And if someone asks us what is codomain of f, that is going to be 1, 2, 3, 4, or the complete set B itself. Similarly, domain will be complete set A itself. So domain will be the first set, codomain will be the second set, and range will be containing only those elements which are mapped or which are a part of the ordered pair. Right? So what I can say is there is a function f defined from set A to set B, right? Such that when you input A, you are getting 3. That means f of A you are getting as 3. So here, A, the image of A is 3. We write down this thing as image of A is 3. So A is mapped to 3. So image of A is 3, whereas A is the pre-image of 3. Try to understand. Pre-image of 3 is A. So image of A is 3 and pre-image of 3 is A. Likewise, if I write down another thing, let's say I have f of C as 2. So this will give us image of C. What is the image of C we are having? Image of C is 2. And similarly, if someone asks us what is pre-image of 2? What is pre-image of 2? That is going to be C. So I hope you will be able to figure out image and pre-image from this discussion, right? So what all we are done with till now? We are done with the definition of function. We are done with what image is, what pre-image is, right? So all these things are sorted till here. One plain and common thing that we'll get multiple times is you will find this term written multiple times. Real valued function. I think the name itself is giving us the clear idea what exactly will be happening in this case. So real valued function means a function which gives the value which are real number, right? So this means output output should be a real number. Output should be a real number. If I write it in different words, what exactly I'll be saying? A function whose whose what? Range. A function whose range, because output is given by range. A function whose range is the set real numbers or or it's a subset of the real numbers. Subset of the real numbers. So either the range has to be the whole real numbers or it has to be a set of real numbers. In that case, we'll be saying that this function is a real valued function. I'll take an example. Let's say we are given f of x as 2x minus 1, right? Where x is a natural number. So we'll be putting different values of x. We'll be getting 2 into 1 minus 1. 2 minus 1 is 1. When I'll be putting 2 here, we'll be getting 2 into 2, 4 minus 1. That is 3. Right? Similarly, when we'll be finding f of 3, we'll be getting 6 minus 1, that is 5. You can see 1, 3, 5, whatever answers we'll be getting over here. This is going to be a subset of the real numbers. And as long as the range is a subset of real numbers, it can be a proper or improper both, right? So that case will be saying this function is going to be a real valued function, right? So till now we have understood what a function is, what domain codomain is, what real value function is. So now, with the help of this arrow diagram, we will be able to identify whether a given relation is function or not. So I'll be taking a question based on that. I'll take a few questions from your book itself, and let's see, let's try to figure out which of the following out of these are going to be function and which of these will not be a function. Just give me a second. I'm bringing the question for you guys. The question is right there on your screen. Okay, so we'll be looking at this question. First question says, which of the following relations are function? We have to find out. Give reasons. If it is a function, determine its domain and range. We are supposed to find the domain and range of a function. Okay, so let's look at the first case. So we are having ordered pair 2, comma 1, 5, comma 1, 8, comma 1, 11, comma 1, 14, comma 1, 17, comma 1. So it kind of looks like that we have 2, 5, 8, 11, 14, and 17 also somewhere. Let's say I'm writing 17 here. These elements are there in the first set, and the second set that we are having, that is containing 1 as one of the element. There might be some other elements, there might not be. Let's say I'm saying there will be minus 2 also. But doesn't matter, that all the elements are mapped to 1 only. So yes, every element is having an image, and every element is having a unique image, right? Like 2 is not mapped to 1 and minus 2, 5 is not mapped to 1 minus 2 or 7 or whatever. Everything is mapped to only 1. So hence this will be a function. I am just marking it as tick. Next part, 2 comma 1, 4 comma 2, 6 comma 3, 8 comma 4, 10 comma 5, 12 comma 6, 14 comma 7. So what you have to do is you have to look at, see, your elements of domain are not repeated. 2, 4, 6, 8, 10, 12, and 14. So elements are going to be 2, 4, 6, 8, 10, 12, and 14. And yes, they are mapped to different elements. This 1, 2, 3, 4, 5, 6, 7. They are mapped to 1, 2, 3, 4, 5, 6, and 7. So yes, you can see each element is mapped. You can see each element is mapped. So, and one element is mapped to only one element, not more than one element. Something like this is given to us. Definitely, this is going to be a function. This is definitely going to be a function. This is a function. It is a, just let me rewrite this part. It is a function. If we look at the last part, what do we have in the last part? 1 comma 3, 1 comma 5, 2 comma 5. So if I draw the arrow diagram for this, we'll be having here 1 and 2 only, and in the other one when we'll be writing, just I'm rearranging this, we are having 3 and 5 here. 1 is mapped to 3, okay, and 1 is mapped to 5 also. I think we should stop our hunt right here, because one element is mapped to more than one element. Definitely not a function. This is not a function. The first two were functions. This was function. This was a function. This is not a function. So just by looking at the ordered pair also, we will be able to comment whether this is a function or no. Right? So that's one of the things that we have defined till now. There is one another method. There is one another method to figure out whether a given graph is a function or not, and that method we known as vertical line test. Vertical line test. Sounds interesting, right? Vertical line test. Okay, what exactly we'll be trying to do here in vertical line test? So let's say if I'm having a graph given to us, graph of any function given to us, let's say something like this, let's say something like this. And if we draw vertical lines over here, something like this, something like this, you can draw as many vertical lines as you want, as many vertical lines as you want, and as long as they're intersecting on only one point. You can see here, you can see here, you can see in this case, and this case. Everywhere you'll be finding that the vertical line is intersecting at only one point. Hence, it is a function. Yes, it is a function. Let's try and see another graph. Let's try and see the graph. So in this, I'm drawing a graph where definitely a vertical line will be intersecting at more than one point, right? You look here, you can see these lines are intersecting at more than one point. That means, let's say if I put this x1 in the output, you'll be getting two different outputs here. If you put x1 in the input, you'll be getting y1 as the output, you'll be getting y2 as the output. Hence, this will not qualify for the definition of a function. This will not be a function. This is not a function, right? So I hope the thing is clear to us. We'll just write this in the statement form. If a vertical line, if a vertical line intersects the graph of a function at exact one point, then it is a function. Then it is a function if it intersects with the vertical line. It means we are talking about the vertical line. If it intersects the graph at more than one point, just give me a second, more than one point, then it is not a function. Then it's not going to be a function. Then it's not going to be a function. So that's exactly the thing that we have here. If a vertical line is intersecting at exactly one point, then it's a function. If it is intersecting at more than one point, then it is not a function. So quickly make a note of this and then we'll be moving ahead. So next important thing that we'll be having is algebra of functions. So next topic that we'll be having here is algebra of functions. Algebra of functions. So what exactly this is very theoretical part. This thing you should be knowing. Let's say if I have f of x, or let's say I'm taking this name, f defined from a set A to the set of real numbers, and of another function g is defined from the same set A to the set of real numbers. If let's say something is there, so you can see one thing, whatever will be the input of this, that will be coming from set A. Similarly, whatever will be the input from here, that will also be coming from the set A. In both the cases, the input is coming from set A, and in both the cases, let's say you have f of x or you have g of x, both output will be real numbers. So this both of these will be giving us the real number output which is a real number, right? So there are few things that we need to define here. If we have to find f plus g of x, that is going to be same as f of x plus g of x. F plus g of x is going to be same as f of x plus g of x. Similarly, if we have to find out f minus g of x, that is going to be f of x minus g of x. Okay. Third, if we have some constant multiplied by f of x, this will be the constant will be coming outside the bracket and we'll be having this as k times of f of x. Next we'll be having here as f into g of x. This is going to be f of x into g of x. And if we look at the division part, if we write it as f by g of x, this is going to be f of x divided by g of x. But there is a condition. There is a condition, g of x should not be equal to 0 for all x belonging to the set A. Whatever input you take from here, you have to make sure that the gx is not giving a 0 value. Because if the g of x is giving a 0 value, then the division will not be defined for this. Then division will not be defined for this. So quickly make a note of this. I'll just get you a simple question where we can use this information and we can figure out all these things that we have discussed in this case. Right. So I'm just taking an example for you guys. I'll take an example from your textbook only. This will help us evaluate what we are looking at. So the question is coming right in front of you here. This is the question and I'm zooming it for you guys. So the question tells us that f of x is x square and g of x is 2x plus 1. This is f and this is g. And we need to find f plus g, f minus g, f into g, f by g. Right. The first thing we'll be calculating f plus g of x. F plus g of x, this will be same as f of x plus g of x. So f of x was x square plus g of x was 2x plus 1. So this is f plus g of x. We can give it any other name if you want. We can call it as any other name if you want. If needed, we can give, or else we can just leave it at x square plus 2x plus 1. Next is f minus g of x. This will be getting as f of x minus g of x. So we'll be getting as x square minus the whole thing 2x plus 1. That's why I have kept 2x plus 1 in the bracket, and we'll be having this as x square minus 2x minus 1. Right. Third thing, f into g of x. F into g of x. That's going to be f of x into g of x. F of x into g of x. Right. This will be giving us x square into 2x plus 1. When we multiply these, we'll be getting 2x cube plus x square. This is going to be your f into g of x. The last one, f by g of x. F by g of x. This is going to be f of x by g of x. So we'll be having here x square by 2x plus 1. So if there is a possibility of cancelling out something, we'll cancel it out, but we'll make sure that the denominator is not becoming 0 because of it. Right? So this is algebra of functions. You might be given this kind of question in your exam. So till now, I think algebra is fine. Vertical line test is fine. We will be able to tell whether a given relation is function or not with the help of the arrow diagram. Right? This mapping, we understood what real valued function is. Domain and codomain, we understood. Right? But sometimes we are supposed to find the domain or range of a function. So I'll just give you some basic tips how to find domain of a function. How to find domain of a function. There are some standard ways how we find the domain of a function. When we are finding domain of a function, what exactly we are doing? We are trying to find the valid inputs. We're trying to find the inputs for which the inputs for which the function is defined. This is what we are trying to find. We are trying to find the inputs for which the function is defined. So there are some standard case. Let's say we are having a function inside the root. Whenever there is a quantity inside the root, we know one thing for sure, that it's not defined for negative values. This will mean that f of x has to be greater than or equal to 0. So this is the thing that we'll be applying. We'll be, let's say a quadratic is given, we'll be making that quadratic greater than or equal to 0. A linear term is given, we'll be making that greater than or equal to 0. Right? So this is one of the method that we use. Now let's say if we are having f of x divided by g of x. So we'll be taking here all the values of x, that we will be taking only those value of x which will not make the denominator 0, or we will firstly put the denominator equal to 0, and then we'll just simply check what values of denominator are making it 0. If I take an example, let's say we are having x square minus 5x plus 6 by 2x minus 3. You can see here that if we want all the feasible values of x or all the possible values of x, then we have to look for a value which doesn't make the denominator 0. Means 2x can't be 3 or x can't be equal to 3 by 2. So that means x can be anything. From a set of real numbers, x can be anything, but x can't be 3 by 2. So x belongs to the set of all reals, but 3 by 2 will be removing from it, because 3 by 2 is making it 0. Right? Next, let's say if we are having 1 over f of x or something, and that too inside the root. A function is inside the root. We know the quantity inside the root has to be greater than equal to 0, but this time it can't be 0. You know why? Because the root of 0 will also be 0. That's why this time this f of x has to be strictly greater than 0. This has to be strictly greater than 0. Okay. Chalo. So let's find the domain of few questions over here. Let's say we have taken one example already. Find the domain of first root of x square minus 4. Second, root of 4 minus x square. Third, root of 4 plus x square. Initially, I'm taking very basic examples for you, right? So we are having root of these quantities. So first case, when we'll be finding the domain for this function, root of x square minus 4. We know that x square minus 4 has to be greater than equal to 0. If we factorize this further, we'll be having this as x minus 2 into x plus 2 greater than equal to 0. And now it comes to the point where we'll be utilizing the understanding of wavy curve. Wavy curve. Yes, we'll be plotting the roots on the number line like this, and we'll be marking alternate plus minus plus. We need it greater than equal to 0. This means us that x has to belong to minus infinity to minus 2 close bracket union 2 to infinity close bracket to infinity. So this is exactly we'll be having for any values here. This root will be defined. If I take any other values between minus 2 and 2, let's say I take 0. 0 square is 0 minus 4 root of minus 4. Not defined, right? So only for these inputs, this expression will be defined. So this is the domain of the function. So let's say if you ask me what is domain, domain is minus infinity to minus 2 union 2 to infinity, right? So this is going to be your domain. Next example, root of 4 minus x square. Again, whatever quantity inside root is, this has to be greater than equal to 0. If I take the whole thing to the other side, we'll be having this as x square minus 4 less than equal to 0. When we plot it, again we'll be getting minus 2, 2 plus minus and plus. This will be giving us x as x belongs to minus 2 to 2. Minus 2 close, 2 also close. So minus 2 close to 2 close. This is going to be domain in this case. Let's say if I take another example, root of 4 plus x square. I think that was the third part, right? Root of 4 plus x square. 4 plus x square has to be greater than equal to 0. You know that x square itself alone is greater than equal to 0. So this quantity is greater than equal to 4. So definitely whatever value of x you take, this will always greater than equal to 0. So x belong to the set of all real numbers. X belong to the set of all real numbers. Whatever you take, whatever number you put minus 1, minus 2, minus 100, plus 100, whatever. This quantity will always be greater than equal to 0. Right? So I hope we have understood how to find domain in this case. Right? I'll give you one question from your textbook. You guys give it a try and then I'll be discussing it afterwards. So the question is coming right on your screen. Here's the question. So look at the question carefully. Find the domain of the function f of x is given to us where f of x is x square plus 2x plus 1 by x square minus 8x plus 12. Give it a try, guys. All right, I think you guys have tried it already. So we'll simplify this. The numerator I can see is x plus 1 whole square. Denominator, if we factorize this, this is going to be x minus 2 into x minus 6. Because minus 2 minus 6 is minus 8 and minus 2 into minus 6 is plus 12. So this is the definition of f of x that we are having. Right now, numerator is defined, denominator is defined, but it might be becoming 0 at few points. So we'll have to remove those points. What are those 2 points? So x minus 2 can't be 0 and x minus 6 can't be 0. So this tells us that x can't be equal to 2 and x can't be equal to 6. Other than these, whatever input you take, whatever value of x you take, the function will be defined, and the function will not be defined for 2 and 6. So this gives us the domain as x belongs to a set of all real numbers except 2 and 6. X belongs to the set of all real numbers except for 2 and 6. So I think we are sorted with this part also. So we now know how to find the domain in such questions. Let's say if we have to find range. So there is a different approach for different kind of questions. Let's say methods to find range. This will majorly, you will be learning this majorly in 12th grade, because there are few concepts of derivative also that you will be using, or increasing and decreasing that you will be using to find the range. So as of now, to your level, up to 11th grade level, what all methods do we need? I'll be telling you this. So let's say this is a quantity, root of x minus 1. Root of x minus 1. We know one thing for sure, that output is going to be greater than equal to 0, because the output of a square root term is never negative. So this has to be greater than equal to 0 for sure. And when will this become 0? F of x is 0 when x is 1. When x is 1. If I take the other values, you can see, if I put x as 3 minus 1 is root 2, 5 minus 1 is root 4, root 6, root 7, the value will be increasing only. So what I can say is the range of this is going to be, so fx will be greater than equal to 0 and less than infinity. Because if I take 1 million, so 1 million minus 1 and root of that, likewise the value will be progressing. This will tell us that the range is going to be from 0 close bracket to infinity open bracket. Right? Now, similarly, we'll look at another example. If let's say we were having f of x as, instead of root of x minus 1, let's say we are having root of 1 minus 6. One thing very sure, we know that x has to be greater than equal to 0. Another thing, this time x 1 minus x has to be greater than equal to 0. This will mean that x has to be less than equal to 1. Less than equal to 1. So less than equal to 1, or what other thing people sometimes mix up here is, they take x less than equal to 1 but only greater than equal to 0. No, greater than equal to 0 is for f of x. This condition is for f of x, not on x. If I put here minus 1000, 1 minus minus 1000, you can see this will be root of 1001. So likewise, minus 1 million, minus 1 billion. So whatever values you'll be putting in the negative, this will be giving you the positive value. This has to be greater than equal to 0. So we are getting again the range as, 0 to infinity. This is the range that we'll be having in this case. I'll find one really good question for you from a textbook if I get one, and that will help us in the understanding of domain and range specifically, right? If I have something, I'll take it for you guys, or else we'll discuss in the next class, right? So I think that's it for now. We have understood what domain and range are. But yeah, before we end up this session, I can just give you one more way. Let's say how to find range of quadratic expressions. Range of quadratic expressions. Range of quadratic expressions you are supposed to find out. So I think you guys are already aware of the fact that the graph of a quadratic, this is a parabola. This is a parabola. And parabola, the exact definition you will be learning in the conic section, but yeah, you've seen it, like it might be upward opening, downward opening, something like this. So this is the function that we'll be having. A general quadratic expression looks like y equals to ax square plus bx plus c, and we are taking abc as real, and a is not equal to 0. The leading coefficient we are taking as non-zero. So if it is not 0, then there will be two cases. First case, I'm taking A as positive. So if A is positive, then the graph is going to be an upward opening parabola. This will be upward opening parabola. Upward opening parabola. Right? This is going to be upward opening parabola. So this is how the graph will look like. Or I'll just try to draw it once again. Something like this. And I'll make a copy of this. Because I'll be using this multiple times. Here and one more time I'll take. You'll understand why I'm making three different copies of this. Right? Now in 10th grade you have studied for a quadratic there might be two real and distinct roots, something like this. There might be real and equal roots, something like this. Right? Something like this, only one root which is repeated root, or there is a possibility, that there are no real roots. This is your x-axis. X-axis. Y-axis can be anywhere. It's none of our concern whether it's on the left side or right side or coming from the middle or whatever. This is your x-axis. So these are your two roots, alpha and beta. These are also two real and equal roots. And in this case, you can see there is no real roots, or we have non-real roots. This is something we are having. So if A is greater than 0, we'll be having two real roots. So this will be the case when D is greater than 0. This will be the case when D is equal to 0, and this is the case. The third one is the case when discriminant is negative or we are getting non-real roots. Okay, so that's the case we have here. Now we have to find their range. We can see the graph will keep going infinitely. Means the upper value is going to be infinite in all the cases. It's going to be infinite in all the cases. And if you just found the vertex of this parabola, the y coordinate, which is going to be minus d over 4a, minus d over 4a to infinity will be your range. This will be your range. Where do we get this from? You'll be understanding this in the chapter of derivatives, like where we'll be finding the derivative of the quadratic expression, and then we'll be taking the differentiation, we'll put it to 0. This is how you'll be getting it. So not concerned for this chapter. You just have to figure out that the range is going to be minus d by 4a to infinity in this case. Right? And if I have to tell you what are the vertices of parabola, not vertices, coordinates of vertex of parabola. So we'll be having here coordinates of vertex of parabola, that is going to be minus b by 2a comma minus d by 4a. This is your y coordinate. This is your y coordinate. Okay, so this will be helping you get the range of quadratic expression. If I take a question based on this, let's say we have y equals to x square minus 5x plus 6. So I told you range you can directly find out. This is the first method. I'll solve this question using two methods. So the first method is we'll be trying to find this using minus d by 4a. What's the discriminant? Discriminant will be b square minus 4ac. So minus 5 square minus 4 into 1 into 6. So 25 minus 24, which is 1. So the range is going to be minus d by 4a to infinity. This is going to be minus 1 by 4 into 1 to infinity. This will be giving us minus 1 by 4 to infinity. Minus 1 by 4 can be attained. That's why we'll be having closed bracket at minus d by 4a or closed bracket at minus 1 by 4. Right? And similarly, we'll make a change here also. This is going to be closed bracket because this value can be attained, or I'll say this value is attained by the quadratic expression, and this is the minimum value in this case. Right? This is one of the method. If I try to do this using completing the square methods, so I have y equals to x square minus 5x plus 6. Okay, this can be written as x whole square minus, I'll be writing this as 2 into something into x. You can see here, this 2 and 2 will get cancelled and we'll be having just minus 5x once again. Now, whatever quantity we have received here, will add its square and we will subtract its square to get the final answer. So this quantity itself, this will be x minus 5 by 2 whole square, and this quantity is going to be minus 25 by 4 plus 6. This will be x minus 5 by 2 whole square minus 25 plus 24 by 6. So this will be x minus 5 by 2 whole square minus 1 by 4. Right? So you can see this method is slightly lengthy. That's why now you'll be admiring, sir. Yeah, definitely we can use minus d by 4a. So this quantity, square root of any real expression, this has to be always greater than equal to 0. So this whole quantity will be greater than equal to minus 1 by 4. And what's the range we are getting from here? Range we are getting is minus 1 by 4 closed to infinity. In this case, this is how we'll be finding the range. Okay. So this is about the first case that we discussed. Let's say, let's take the other case where the leading coefficient is negative. We told initially leading coefficient can't be zero. Either it has to be positive or it has to be negative. We discussed all the cases of positive and now we are going to discuss the cases of negative. Let me try to draw a decent looking parabola for you guys. A downward opening decent parabola for you guys. So I'll make multiple copies of this. Come here and one more copy. Again, same thing. There might be two real roots. There will be real repeated roots. There might be no real root. So same three cases can be there. D greater than 0, D equal to 0, D less than 0. So in this case, the only difference that you will be having here is that the minimum value is minus infinity. In all the three cases, the minimum value is minus infinity and the upper value, the highest value that it can attain is the y coordinate of vertex of the parabola, y coordinate of the vertex of parabola. That's going to be minus d by 4a. Value remains the same, just this time it's minus infinity to minus d by 4a. In the previous case, it was minus d by 4a to plus infinity. Right? So this is how we can find the range of quadratic expressions. I have used one example. I have shown you with the help of one example how we can find it. I hope you guys will be able to do things from here. So that's it for today and I'll see you in the next video. Till then, take care. Bye bye.